Hi, Chem 100. This is a topic video on a third way to do limiting reagent question. It's called the looking at the question through the normalized molar amount. So the normalized molar amount we're going to call NMA, and it's going to be a third way to do the problems. It's going to compete. You get to choose if you like this way better with doing it the foolproof way, which is if you have a chemical reaction like this, and you have the amounts either in moles or in grams of more than one of the materials, you don't know which one of you're going to run out of first. So we said the foolproof way is to take this 20 grams of methane, take it all the way to the product that you're interested in. So let's say we want to find out how much carbon dioxide we could possibly make if we started with 20 grams of methane and 20 grams of oxygen. You can't tell right away which one of these two things you're going to run out of first. So what you do is you take the 20 grams, you go through the stoichiometry, and you relate it to how much carbon dioxide you can make, you get a value. Then you take the 20 grams of oxygen, you run it through the stoichiometry, and you get a number. You have those two numbers, you compare them. The smaller one we said was the correct one. The larger one never happened because you already ran out of the other material. The one that gave you the smaller answer is called the limiting reagent. It's the material that you ran out of first. So that was one way to do it. A second way to do it was to make a table where you put down in moles the initial amount of each of the reactants and the products, how much they changed by, and what you had at the end. Okay, so these are, a lot of times people do these in Chem 2, and it's initial change in equilibrium. Here we're just going to call it initial change at end. So we need to convert the two materials into moles, and then we need to do a little analysis of how much of this reacts with how much of this to create such and such of this and such of that. So that was the second way that we did it. So this third way, you can pretty quickly determine which stuff you're going to run out of first by converting all of the reactant materials to moles and then dividing them by whatever their stoichiometric coefficient is. So for instance, I would take this 20 grams, convert it to moles by dividing by its molar mass. Once I had its molar mass, I would divide it by 1 because its coefficient is 1. That value, where you divide by the coefficient, is called the normalized molar amount, and we'll read the definition in a second. Over here, I would take the 20 grams of oxygen, I would divide it by its molar mass to give you moles, and then I would take that number of moles, and divide it by 2. That would be the normalized molar amount of oxygen. Then I compare those two normalized molar amounts. Well, I already factored in or baked in the coefficients. So I don't have to worry about, oh, it takes 2 of these to react with 1 of those. I just look at those normalized molar amounts, and whichever one is smaller, that's the one that's going to give you the correct amount of product. That's the one that's the limiting reagent. So we're going to do this problem in a second after we look at the definition. So the normalized molar amount, NMA, is the amount of a reactant in moles divided by its coefficient in the balanced chemical equation. The reactant with the smallest NMA is the limiting reagent. Okay? Sometimes you might have two things that are tied. Okay? Two things come out and they have the same exact number of moles. Well, then both of them are the limiting reagent. You're going to run out of them at the same time. So here's an example of a chemical reaction. Small a is the coefficient on the chemical A, small b is the coefficient on B, small c is the coefficient on C, and small d is the coefficient on D. So if I want to find out the normalized molar amount of any of these things, I take the moles of this divided by A, the moles of this divided by B, the moles of this divided by C, the moles of this divided by D. If I want to compare the normalized molar amounts of one with any other one, I just take those normalized molar amounts and look at them. Whichever is smaller, that one would be the limiting reagent. If I have 3 things over here, it doesn't matter. If I had an X over here, I would take its coefficient and divide the number of moles of X that I started with by whatever its coefficient is. Sometimes it's not, you don't have 1s and 2s, which are easy to rationalize. Oh, I need twice as much of this as this. Sometimes you have like a 2 and a 7. So it really does come in handy where you would just take A divided by 2 if that was its coefficient, and B divided by 7. You don't have to worry about. Whichever one comes out smaller is the normalized molar amount. So the NMA for substance A is equal to the moles of A divided by A. And you get the moles from the grams using the molar mass like we learned before. Okay, so that's all I have for notes. So we're going to do this one question using this technique. Okay, so our coefficients here, this is already balanced. This is the combustion of methane. One methane creates one carbon dioxide. So if I'm interested in finding out what is the maximum amount of grams of carbon dioxide I can make if I started with a chamber that had these amounts of starting materials, 20 grams worth of methane and 20 grams worth of oxygen. So the way I do it is I first calculate the molar masses, and I wanted to save some time, so I already did that. So we know, we've seen this before, the molar mass for methane based on its atomic masses is 16 grams per mole. The molar mass for oxygen is 32, carbon dioxide is 44, and water is 18. 16 plus 1 to gives you 18. Okay? So we'll get back to those in a second. So starting with the first one, the methane, let me get this right up in here so you have enough space. Let me just move this down a little bit. So I'm not falling off the desk. So I start with my 20.0 grams of CH4. Want to change it to moles. So I grab my molar mass. The magic number for methane is 16 grams for every mole. So that goes in the denominator there. 16 grams for every 1 mole. That's the magic number for methane. This is going to give me the moles of methane. So I can calculate that. So 20 divided by 16 gives me 1.25 moles. Okay? Now, if I divide it by its coefficient, this guy's coefficient, this is a 1 here, so I put a 1 here, the normalized molar amount is 1.25, right? So the normalized molar amount of methane is 1.25. Okay, do the same thing for oxygen, right? Just happen to start with 20. This could be any number that I decide as the teacher to give you. It could be 40, 70, 11.4, 1.3, whatever you want. This is how much you have in the cupboard. There's nothing special that they had to be equal to each other. It's just the way I chose to write the problem. Okay, so for my 20.0 grams of oxygen, oxygen is going to be heavier. Turns out that it takes 32 grams to make a mole for O2. So 20 divided by 32 is going to give me the moles of oxygen. Then I'm going to divide by 2 to get the normalized molar amount. So I have 20 divided by 32. That gives me 0.625 moles. Then the normalized molar amount for O2 is 0.625 moles divided by the coefficient 2. Where's this 2 come from? That's this 2 up here. So I'm going to make this a little bit smaller. You can see the whole page then. Okay, so that 2 comes from there. That 1 is that 1. Okay, so the normalized molar amount, you're dividing by the number of moles. Okay, so 6.25 is going to give me 0.13. This is the smaller of the 2 numbers. So I'm going to run out of oxygen first. So oxygen is the limiting reagent. Now that I know that oxygen is the limiting reagent, I could have go back, start with the 20 grams of oxygen and do my regular stoichiometry and relate it to the amount of carbon dioxide that I started with. But I'm kind of halfway there with this normalized molar amount. You see, I've already divided by the 2 for oxygen. So all I have to do now is relate that normalized molar amount to the amount, this coefficient over here, and be able to calculate the amount of carbon dioxide. So this 313 moles, if it's normalized moles, meaning I already factored into of oxygen, all I have to do is multiply it by, that creates whatever this coefficient here, and this denominator will always be 1 normalized, right? We already took care of the coefficient back here. Okay, so this will always be 1, and then why is this 1? Because this is 1. And that's going to make carbon dioxide, and if I want grams of carbon dioxide, the magic number for carbon dioxide is 44, right? We've seen that many times. 44 grams to make a mole of carbon dioxide. 44 goes in the numerator. 44 grams makes 1 mole. So this is going to give me another way to figure out how much carbon dioxide I have. Okay, then what we can do is, because we've got 3 out of 4, we can go ahead, right, and, well, let's go ahead and get this answer first. So I have 0.313 times 1 divided by 1, doesn't change anything, times 44. So 0.313 times 44. So I'm able to make only 13.77, right? So I'm going to make that 13.8 grams of CO2. Okay. So this guy turns out to be 13.8 grams that I can make over there. So it's no longer a question mark. I figured it out. Move it up a little bit. Now, not ready to do conservation of mass yet, because I don't know, I didn't calculate how much of the 20 of this guy's gone, right? All 20 of these have been used up. But I don't know, there's some left over here, so not going to be so easy. I need to do one more step. I need to actually calculate how much of this was used up, or calculate how much of this was created. Okay, if I can calculate how much of this was created, then I know the amount of this plus this that was created has to be this that was used up, which we know is 20 because I ran out of it, and I can get how much of the other one was used up. Okay, so let's go ahead and calculate this one first, because we're almost there, right? So if I want that in grams, okay? Now, easy part is I already know that oxygen is the limiting reagent, and I actually already know how many moles of oxygen I have, okay? So I can go all the way back to there, how many moles of oxygen I have, and I could do the stoichiometry based on that. I could save some steps, so I'll show you that. So this is 625. Again, nobody's stopping you from going back to the beginning if you're so used to going back to the beginning. You take your 20 grams, divide by the 32 grams per mole, relate this guy to this guy. But I've got this guy right here, okay? So we know that you're running out of this, so I can relate it to that, right? So since I'm already in moles, I can go directly to the balanced equation. 2 moles of this creates 2 moles of that. That's a 2-to-2 relationship. Okay, not doing the molarized, normalized molar amount now, because I already know the limiting reagent. Okay, so this is going to make water, and I just got this one down here wrong. This is from oxygen. Okay, and if I want grams of water, magic number, seen this so many times, 18 grams is equivalent to 1 mole for water. So I'm going to take my moles of oxygen, 2 divided by 2 cancels out, and just multiply it by 18. So I got 0.625 times 18. That gives me 11.25 grams of water that was co-created with the carbon dioxide. So this question mark can come out, and I've just figured that out, right? So this is 11.25, and I'm going to round this to just one place after the decimal. So 11.25, let's round that to 11.3. Okay, so if I add this 2 up, the total mass, we can do conservation of mass now to see how much of this must have co-reacted or reacted with the 20 grams of oxygen. Then the last thing, we can check ourselves by doing the stoichiometry between this one and this one. So let's add these two up. I got 13.8 plus 11.3. That gives me 25.2. See, it's a lot less than the 40 that I started with. 25.1. Okay, so how much methane must I use? Well, I know I used all 30 of this, right? This is all used. So how much of this must have been used by conservation of mass? What goes in must come out. So this has got to be 5.1 grams, because this guy is a perfect 20. So 20 plus 5.1 grams of methane that was used up has to equal the 25 grams that was created, where this one is 13. Sorry about that. This one is 13, and this one is 11.3. Okay. All right, last step. If this is true, right, out of my 20, how much would be left in the pile at the end? Well, there would be 14.9 left over. 14.9 grams of methane left over. I don't use very much of it at all. Okay, so I really ran out of oxygen way early in the process. Okay, well, let's just double check that. Well, one way to double check that is you can go back and relate this to this, right? You can not only relate a reactant to a product, you can relate one reactant to another reactant, or even one product to another product. If you make so much of this, you can ask yourself how much of this you can make without ever going back and looking at these. It's always two at a time. That's the cool thing about stoichiometry. Once you find out what you ran out of first, that's the driver. This really doesn't matter much anymore. This 20 drives the whole show. Okay, so for this particular one, let's go back to the beginning. Okay, so I have 20 grams of oxygen. Okay, you're so used to doing them. You know what, a lot of people just go back right to the beginning. There are 32.0 grams in every 1 mole of O2. That's the molar mass. That's the first step, get the moles, right? Goodbye grams. Okay, next step, look at the balanced equation. This is a 2-to-1 relationship. For every 2 moles of O2 that I use up, I also use up 1 mole of methane. Okay, so yes, you can relate 2 reactants. Okay, can you guys see that? All right, what do I need up here? I need my magic number for methane, which we did before. Its molar mass is 16. 16 goes in the numerator. 16 grams, make 1 mole for methane. Okay, so I'm hoping if I did this right, I better get 5.1 grams, right? So there's a whole bunch of ways to go around in a circle that everything has got to match up. Okay, the last way you can do the whole thing in a table of moles would be another way to do this. So there's 20 divided by 32. Gives me my 0.625 again. Take that, divide it by 2. That gives my molar, normalized molar amount again, times 16. And this time, instead of getting 5.1, I get exactly 5, okay? And that's just a rounding error in there someplace. 5 grams of CH4 used up. Okay, so everything pretty much matches up, right? 5.1 is close enough to 5, and the 20 equals 13.8, and the 11.2. These two have to add up to these two. Good? Okay, that's it for normalized molar amount. It's just another way of doing it. If you like it, do it that way. If you don't have to.